Number 1, write an equation that would model a population with an initial size of 625 that is growing at an annual rate of 8.5%. So let's define some variables here while we're at it. We'll say t is the time in years after the initial population, and we'll say p of t is the population. So p of t, the population t years from now, is, well, I'm starting with 625. It's just like compounding interest because I have an annual rate of 8.5%. So 1 plus 0.085 raised to the t. That's our yearly rate. That's after t years. So p of t equals 625 times 1 plus 0.085 to the t represents this model. Number 2, as water drains out of a pool, the depth of the water decreases at a constant percent rate of change of 20% per hour. Whenever something's changing at a constant percent rate, that's key for exponential function. The depth of the water when draining begins is 12 feet. Find the depth of the water after 7 feet. So I'm decreasing the amount of water, so this is a decay function. This function is decaying. So I'm starting at 12 feet, times 1, I'm losing 20%, so 1 minus 0.2 raised to the t, where t is hours, equals, we'll just call it the height of the water, the depth of the water, we'll call it d of t. So t equals hours. Because it's 20% per hour, t is hours, those match up. So after 7 hours, d of 7 equals 12 times 1 minus 0.20 to the 7. So if you did 1 minus 0.20, you would see that it's 12 times 0.8 to the 7, which makes sense because if we're losing 20%, we're keeping 80% of it. So 12 times 0.8 raised to the 7. After 7 hours, there's about 2.5 feet of water left. Approximately 2.5 feet of water is the depth. So be careful when it's decay functions if it's decreasing. Exponential functions model that constant percent rate of change. There are 400 bacteria in a petri dish. The number of bacteria in the dish triple every 4 hours. So whenever something's tripling or doubling or decaying by a third, or whenever I'm decaying by that constant percent or that constant ratio, I need to use an exponential function. So b of t, my initial is 400. If I'm tripling it, my multiplier is going to be times 3. If I was doubling it, my multiplier would be times 2. But I can't just raise it to the t hours, because t is hours. And I don't want to triple every hour. I want to triple every 4 hours. So I'm going to do t divided by 4. That way, when I plug in a 4, 4 divided by 4 is 1, I triple it once. So to deal with that every 4 hours, I do t divided by 4. That's our function there. How many bacteria are in the dish after 10 hours? Well, t is hours, so b of 10 equals 400 times 3 to the 10 over 4. That'll tell me how many bacteria are there. 400 times 3 raised to the 10 divided by 4. Could have done that first, got 2.5, but there's going to be about 6,235. We'll just round to the nearest bacteria. 6,235 bacteria approximately after 10 hours. The key here is you need to watch out for it doesn't just triple every hour, it triples every 4 hours. So I dealt with that by dividing that exponent by 4. Hydrogen-3 has a half-life of 12.31 years. Consider a 50-gram sample of hydrogen-3. Write a function for h of t, the amount of hydrogen-3 left after t years. Okay, so half-lives are exponential decay. I keep losing half of it. So that half is my base. I'm starting with 50 grams, and I keep multiplying it by 1/2. But I don't want that to happen. I don't want that 1/2 to happen every year. I want it to happen every 12.31 years. So I'm going to do 1/2 to the t divided by 12.31. That way, if I plug in 12.31, I lose half, because my exponent will be 1. If I plug in 24.62, my exponent will be 2, so I'll lose a half twice. Make sure you write the function h of t, the equation there. So that's my equation. 50, that's my initial amount, 1/2, because it's a half-life problem, to the t over 12.31. How many grams of hydrogen-3 remain after 30 years? Everyone's favorite game, plug it in. Plug in 30, 1/2 to the 30 divided by 12.31. So let's go to our calculator and do 50 times, if you have a fraction button, you can use the fraction button here, alpha y equals enter, or just do 1 divided by 2. You can do it the right way, unlike I've been doing. 1/2 raised to the, and if you want to use the exponent again button up here, the fraction button again, that's fine. 30 divided by 12.31. So that 12.31, that's how long it takes to do one whole half-life. We hit enter, and we get 9.2333. Does it tell us where to round? How many grams? It doesn't. So about 9.233. There's about 9.233 grams left of hydrogen-3. The rest of it decayed to some other element, but we're left with 9.233 grams of hydrogen-3 after 30 years. Determine and state the yearly percent rate of change for hydrogen-3. So I want the yearly percent rate of change. So we need to somehow manipulate our exponential model here. This is our model that we've been using. This isn't the yearly rate of change, though. This is how much it changes every 12.31 years. So let's use a power to a power property. Let's do 1/2 raised to the 1 over. So let's do the 1 over 1.31, then raise that to the t. So let's deal with that dividing by 12.31 first. So let's do 1/2 to the 1 over 12.31. Should stop hitting the button too many times. Nope. Let me just use my finger instead of my pen. 1/2 to the 1 over 12.31. That's actually what the base is. The base is actually 50 times about 0.45, about 0.945 raised to the t. These functions are approximately equivalent. This function and my original function, these are approximately equivalent because I rounded, so that's why it's approximately, but they're the same. I just used a property of exponent to change the way that it looks. So what's the yearly percent rate of change? Well, that's 1 minus my rate gives me that decimal. So how much did I lose? So if I subtract that 1 over, I get 1 minus that answer. To make it a percent, I'm going to multiply by 100 because that's the rate. So I get 5.475%. It's about, R equals about 5.475. So every year, we lose about 5.475% of the hydrogen-3. That's the yearly percent rate of change that, after 12.31 times that happens every year, you end up with your desired half-life. So if you ever want to find the yearly percent rate of change, or if you ever want to find the percentage, you have to do the base to whatever that exponent is, and just so the exponent is t, just so that you have nothing left in that exponent, do the base to whatever else is happening to that exponent by using power to a power.